the title for today is Motion Planning as Search. Okay, so last time we talked about humanoids, right? And we, in the progression of the class, we have talked about relatively simple systems. We went through the model under actuated systems. We went through the simple walking robots. We understood a lot about the nonlinear dynamics and control. And then with the last lecture, we started getting into more complicated robots, humanoids that have many degrees of freedom. In some ways, like I said, that actually makes control easier and planning easier, because you can start using simple models and have your many degree of freedom robot act like a very simple system, roughly like a missile, if you will, or something, some simple system at the center of mass, and you can realize a simple system with your many degrees of freedom. But, as you will see on the slides in a minute, when you have many degrees of freedom, you can also get into more trouble, right? So having lots of degrees of freedom means that you can get into planning problems that look more like geometric puzzles, okay? A compass gate can only do so much and can only get into some, a handful of situations, but a full humanoid might need to reach into the bag and solve some pretty complicated motion planning problem. Now, a few of you have taken the manipulation class with me. We talked a bit about the motion planning algorithms for manipulation, which were mostly kinematic motion planning problems. Okay, so we just think about a series of positions that were feasible and collision-free over time. And the goal for today is to take some of those basic ideas and extend them into the dynamic realm. So how would you take, let's say if you've seen sampling-based motion planning, how do you take a sampling-based motion planning and add dynamic constraints? So if the system's under-actuated, you can still make those kind of things work. So I'll riff on something slightly different first. So AI planning has a huge history in artificial intelligence, right? The first piece of artificial intelligence research ever was like Samuel's checker players, right? Solving classic games like checkers and eventually chess and all these other things. These were the core of AI. And many people actually, for a long time, said that the route to AGI, if you will, was to build ontologies of information. There was a guy, Doug Lenat, who had people typing in dogs are chase cats and cats chase mice and core knowledge into some big database. And then if we could have very efficient search algorithms that could search those databases, then eventually we'd have sort of general intelligence. Hey, it moved.
All right,
that's a good sign, right? And ironically, in this day and age, something different happened, but it's not so different, right? It turns out that reading everything on the internet seems to somehow have gotten us to something that looks a bit like what the early AI people were talking about in terms of general intelligence. Okay, so, but it doesn't solve every problem yet. Like the large language models don't solve every problem yet. So let me just catch up with myself here. So these are the kind of problems you might get into if you're a humanoid. This was Atlas. We actually had to do this. We had to plan trajectories of getting boards out of there was one situation in the DARPA challenge where there were 2x4s going to be thrown down in front of a board, and you had to clear the boards and then get through the door. So we had to make motion planning solutions that would basically play Jenga, roughly, and pull these things out. It was actually really funny. There was one day in the competition where we picked up a board and moved it aside, and then we went to open the hand, but one of the cables in the hand had snapped, right? So we couldn't actually let go of the board. So we had to go through the rest of the competition holding a frickin' 2x4, right? And we're doing everything with our left hand and carrying around a 2x4 just because our cable snapped. Okay, so this has been a long time. So James Kuffner was one of the people who invented a lot of made some of the seminal contributions to the algorithms we'll talk about today. And James was very interested in humanoids, actually, and we'll talk a little bit about how these things work. But this is the kind of problem that we want to solve today, is having a robot that has some dynamic constraints, but is also solving a geometric puzzle of trying to reach down and avoid collisions and grabbing a flashlight. In the ontology of sort of approaches in the class, these problems can look a lot like geometric puzzles. These are the sort of classic geometric puzzles, and actually there's a great book by Steve Laval on these methods. We'll get into the more kinodynamic versions of these. Okay. In the ontology of things for class, we talked about flying a quadrotor through a forest. This was a trajectory optimization approach, right? And it happened to work well in this particular instance, but we weren't guaranteed to find a solution if it did exist because of the local minima and the trajectory optimization problem, right? So if we were to instead have a more complete, stronger planning algorithm, then we might have different properties, like we would find a solution if it does exist, okay? And we're going to leverage these larger scale AI planning ideas to make that happen, but we're going to try to figure out how to put in dynamic constraints. Okay, so large language models have changed our world in the last few days. So I thought, what the heck? I have a quadrotor at position 000 or 001. There's there are 5 meter tall, 0.5 diameter trees located at these positions, giving the coordinates, okay? The quadrotor is 0.1 meters diameter. What path should the quadrotor take to get to the goal, right? Oh my God, you wouldn't believe what it says, right? It gave me a perfectly good answer. It happened to basically fly above the trees, which wasn't what I was going for, but that's my bad. I would have written a better, But down to the coordinates, that's a feasible plan, right? It actually backs up, flies over, and then goes down, right? Really good, really good. Okay, so, but that's my bad. I would have, I write optimization problems for a living, so I would have given a fully formed problem if I had thought it was going to do this well. So, so that's on me. But I said, okay, well, can you find me the shortest path, right? It still flies above the trees, so it's not solving. It hasn't replaced us yet, but it's really, really, really good. Okay, so the word on the street for these models is that they do solve incredibly rich, borderline intelligent problems. They don't do, one of the metrics that people measure is how well they do long-term planning and sequential planning and stuff like this. And they're deficient in that way. They can't solve, they can give you a recipe that has many steps, but if there's a large branching factor, right, of like all the different things you might have to do, find your way through a maze or something like this, this is one of the places that people feel that this is not solving that problem yet. But ChatGPT can use tools, right? So you can imagine, I think one of the ways this might go is that you prompt engineer your way into saying, call a planner, right? Solve a harder problem. Okay, but there are very, very good planners from the AI world that can help solve these problems. Historically, those planners were discrete, right? So it's when we talked about dynamic programming, we started dynamic programming as discrete graph search. If you think about having enormous graphs, just absolutely, you would never put the graph in memory. It's too big. But can you find good approximate solutions? The AI community has been banging on that for decades and decades, and they work beyond reason, big problems, okay? But they haven't historically, stop. I just rebooted my machine, so it's, stop. They haven't historically solved the continuous problems that we have in robotics. Okay, so today we're going to try to make that connection clear. So let me, I can't assume everybody knows the kinematic motion planning, so let me say a little bit about kinematic motion planning just to set the stage, but we're going to spend most of the time thinking about how to add dynamic elements to the kinematic motion planners, okay? So, if we have very good graph search tools, but we have a problem whose domain is in the joint angles of the robot, how do we connect our two worlds? Okay, so the canonical picture would be, imagine I have, let's say, two joint angles, or so it's not phase space, it's just two joint angles. And I've got some obstacles that I want to avoid. Okay. In the world, and I might have a start configuration and a goal configuration. How do I find a path from the start to the goal? That's not a very hard instance, I guess. I gave myself randomly. Maybe this is a better one. Okay, and maybe I'd want it to find something that will find a path from the start to the goal. The discrete graph search, if I tell you that the discrete graph searches algorithms are extremely good, then you could immediately think about things like, let's discretize the state space, like we did with dynamic programming, and make edges. You know, we would just remove the cells that were in collision, and then make edges to the neighbors, and just solve our dynamic programming problem. But unless your obstacles line up beautifully with your discretization, there's some problems with that approach. In particular, that approach would not necessarily be complete, right? So for a planner to be we'd like a planning algorithm to be complete in the sense that if there exists a path from the start to the goal, then the algorithm will find one with probability 1, let's say. Okay? And you can imagine if I have a discretization, maybe I need one more color of chalk here. If I have a discretization that somehow lines up, maybe I have a very narrow corridor here. Let me extend this obstacle a little bit just to make my point. Okay, a very narrow corridor, and my discretization got a little bit unlucky here, okay? It might be that I have to mark this as occupied, and I mark this as occupied, and I mark this as occupied because of my discretization, and even though a path did exist that would have gone through there, my discrete search would never find it. Okay, so in terms of complicated spaces, discretization, and we also know there's limits to how high dimensional we want to discretize, but discretization might not be the right answer. So there's a different idea, which has become incredibly powerful and widely used in robotics, is to do sampling-based planning. And I want to start there today. Okay, how many people have heard of probabilistic roadmaps? Okay, good. All right, so here's a similar problem instance, and here's a very simple algorithm that has this nice property of getting towards completeness. We'll think about exactly what the completeness statement would be, but let's say instead of discretizing on a discrete grid, I'll just draw random samples in the configuration space, okay? And I'm going to make edges to any collision-free edge to my neighbors that I'll add, so I'll add that to the graph. If I sample arbitrarily often, right, as the number of samples goes to infinity, similarly as the discretization goes to infinity, but this tends to scale better. As my number of samples goes to infinity, I'll eventually have the property that I can find a path if it exists. Okay? The algorithm really is extremely simple. The first thing I do is I build a roadmap where I just start with an empty graph. I just start sampling random configurations. If I sample a random configuration and it happens to be inside an obstacle, then I'll just reject that sample, okay? And that's an easy check with our collision engines that we already have, even in our big robot problems. We can quickly query whether a sample is feasible or infeasible. So I'll just repeat this random sampling of a configuration until Q is collision free. And then once I've got that, I'll insert that in my graph. And then afterwards, I'll go through, and for all of the Q's in the V, I'll find all the nearest neighbors up to some range, and I'll try to add an edge. If I can successfully add the edge with, if I could maybe check along the line segment to see if there's any collisions, then I'll add that to my graph. And now I've got a graph over the continuous space, which looks something like this. I get a new start, a new goal, and I can just run a graph search algorithm to try to find the start to the goal. Yes?
When we check the collisions along the edge, are we doing like a continuous check, or is that also different?
Almost always so the question is, what are we doing to do the collision check along the edge? Almost always people just sample finely along the edge because we have good tools for collision checking. There are better tools to do it exactly. You can do sums of squares to do it, actually. You can, people do swept volume collisions, for instance, which would tend to be conservative, but correct. There's lots of different ways you can do that. Most of the time, people just sample, and then every once in a while, you clip a corner. Okay, it happens. Yes?
It doesn't really seem efficient to me to have to check every single other point to see if you can connect to it. Is there a way you can just search nearby points?
I'm sorry, it's just you have some nearest neighbors.
Oh, okay.
Yeah, exactly right. So you take some volume, that's a parameter that you tend to set as some threshold on nearest neighbors, either by number of neighbors or by distance, and use that. And people build they use KD trees and all the right data structures to make that efficient. Yeah?
Do you typically just sample some large number of points first and then connect them all together and then search, or is it like you sample some number, you search through it and see if it's possible?
Yeah, that's a great question. So in the probabilistic roadmap, I think the probabilistic roadmap, which is my sort of opening bid here, it's often used in this sort of multi-query fashion. So you often do one initial dense sampling of the space and build a graph. And then when you have a new start and a new goal, you try to connect it up. If you were unsuccessful connecting, you could try to add more samples. If you think a path exists, but you weren't able to find a path, then you could try to add new samples and try to have a repair step that tries to repair the roadmap or improve the roadmap. But the second algorithm we'll talk about is very much, will keep expanding until you find a path. Yeah, but that's a good question. This one tends to be good if you're going to solve many queries on the same environment. Maybe you're a robot making salads and you're working in the same space all the time, but you have to go different starts to different goals because you're different ingredients or something like this, then that's a multi-query setting.
Is uniform sampling often what people use, or can you bias it towards the thin corridors between?
That's a really great question. So the simplest version of this would be you'd sample uniformly. If you reject samples inside here, then actually the distribution, you can think of that as an algorithm for sampling from the distribution, which is the free space, which is pretty elegant actually, okay? Yes, there's lots of work on trying to bias samples towards narrow corridors and things like that. What we'll talk about today is thinking about ways to change the sampling distribution to respect the dynamics, which is, I think, more important. You'll see that the uniform sampler can be very bad for systems with dynamics. Awesome questions. Okay, so the algorithm is probabilistically complete. Now, this is a caveat here. It's probabilistically complete. Didn't give myself enough space. Probabilistically complete, meaning that as the number of samples goes to infinity, I will have a complete algorithm. Okay. It's actually interesting to ask how well this scales, right? So people will, I think, fairly routinely use these algorithms up to, let's say, certainly a 7 degree of freedom robot arm. That's one of the most common use cases. You see that it doesn't necessarily find the shortest path. It will find the shortest path on the graph, but that might not be the shortest path in the continuous space. So sometimes you'll see robots do the sampling-based motion planning dance. There's a really good toolbox called MoveIt. That's one of the things people use in the ROS world for this. In the MoveIt demo reel, the robot's going like this to set down an object. Oh, drives me nuts. But it doesn't find a perfectly short path, but it's actually solving a pretty good problem. I see people using it in like 10 dimensions. It seems sort of fairly reasonable. I don't see people using it for 2 arms, for instance, which would be like 14 dimensions. Or if you have a mobile base in 2 arms, 17 dimensions, that kind of blows the stack. Sampling at that high of a dimensional space doesn't seem to work super well. So people will use heuristics like I'll find a path for the first arm, and then I'll use that as a movable obstacle for the second arm. Okay. So 10, I think, is a fairly fair number for the state of the art today. It's bigger than we could do value iteration on with the discretization approach, but it's not, maybe solving everything yet. Okay, so what if I had dynamic constraints? Oh, yeah.
This is all in joint space, right? So if you have an obstacle, you have to project it into joint space.
So, great question. So in the toy problem here, this would be like a point robot moving through the two-dimensional space. If your robot has geometry, then we're thinking about this in being in configuration space. So even if you're a point robot, then the configuration space would be, you would add the geometry of the image of your geometry into the obstacles, and then you could plan points through that. You could think, if you prefer to think about it, you might never need an explicit representation. In fact, normally you don't need an explicit representation of the geometry. You just need to be able to answer the query, is this configuration in collision? So in practice, we just have a collision engine. Everybody has geometry. Even in joint space, where these are harder to picture, right? We're just asking a Boolean question. Does that, in this configuration, I can put things into world space and ask the collision query. Okay, so what if we have dynamic constraints? Let's say, would this algorithm, let's say, solve the pendulum? Okay, even just the pendulum swing up. Just a quick thought experiment, right? So I've got my now I've got a phase portrait, right? You know the phase portrait of the pendulum well. Okay. Let's say I started picking random points, just sampling random points in state space, and then trying to connect them up. Okay. What works and what doesn't work about the algorithm? Well, the first question, and so the nearest neighbor algorithm got a lot more interesting, right? So, if I have these 2 states, are they nearest neighbors or not, right? Or let's say if I ask for the nearest neighbors of this state, right? Are both of those states nearest neighbors? Okay. You know that things move around in this direction in phase space, right? So if I'm at this state, then getting to that state seems very tractable. Getting to that state does not. You have to go all the way around the circle to get to that. So I wouldn't want to call that a nearest neighbor. But the standard Euclidean metrics for nearest neighbors would try to group those into the same. Okay. That example also points out there's an asymmetry in the sampling, in the distance query, right? So where we talked about undirected graphs on the PRM, we're now going to want to have directed graphs and somehow say that this one is a neighbor, but maybe I want like this, but I don't want the arrow to go both directions. That would be a false premise. Okay, so some of the challenges with making these sampling-based algorithms work with dynamic constraints were actually, even though people don't recognize it for that, these were some of the challenges that first motivated the invention of the RRT, which is another sample-based motion planning approach. So that was the probabilistic roadmap, and now we're going to do the RRT, rapidly exploring randomized trees. Okay. The rapidly exploring random trees algorithm is very similar to what we did already, but we're going to do it in not a multi-query setting. We're going to do sort of, I've got an initial state, I've got a goal, and I'm going to start growing a tree out from the start to the goal. So imagine that this is my initial point, or I've now started to grow some particular tree, but the recursion is sort of easy to see. Imagine I've got myself in a particular configuration with a handful of nodes on the tree. And what I'm going to do is I'll pick a new point at random, look on the tree, even if it's not near in terms of some Euclidean distance, I'm going to say I'm going to find the closest point on the current tree, and then I'll add a new node in the direction of the tree, direction of that random state. Okay, so instead of uniformly covering the state and trying to connect them up, I'm going to actually just grow out from the beginning. Why does that help with the dynamics case, right? Is I could imagine only growing out in the directions that were dynamically feasible. Okay, we're going to see how that plays out in just a second. What's amazing is that these algorithms have some really, really nice properties. First, let's understand those properties in the just purely kinematic case. Okay, so these random trees start growing out and will eventually, as probability, as the number of samples goes to infinity, with probability 1, they'll cover the entire space, the entire collision-free space. So some of the problems that have narrow corridors, that are that are classically hard for some of the sampling-based planners, they're actually good in the sense that they will eventually, with enough samples, find a path from the start to the goal. I spent a little time making Meshcat work for that, so I'm going to make you watch it. Not just that, but you can look at that, right? It's pretty good. And you can do the bug trap too, right? Woo, like that. Okay, that's pretty good. Okay, so let's just understand that basic algorithm first in the kinematic sense, and then think about how to extend it into the dynamic case. So there's two things to know. The first one, is that it's actually doing something very clever. Even though the algorithm was very simple, pick a point at random, find the closest node, and then expand towards it. Not every random algorithm works well. That was a very special, careful case of it. So this naive sampling, if that algorithm on the left was basically pick a random vertex on the tree, grow it in a random direction. Repeat, right? That seems like a similarly inspired algorithm, okay? But it performs very differently in practice. That's how you get these hairballs over here, right? Picking a random point and growing in random direction somehow doesn't capture the fact that you really want to explore space. And in practice, it'll tend to do a random walk around the origin, and only with low probability eventually expand. The RRT algorithm does something different, right? It picks a random point uniformly and tries to use that as a sub-goal to grow the tree towards that. What's amazing is that gives the RRT something called the Voronoi bias. Okay, so do you guys know what a Voronoi region is? Let me see if I can reset that. Okay, so imagine I've got a little bit of a tree here. If you just have a bunch of points in a 2D space, for instance, you can define the Voronoi regions. The Voronoi regions are the regions of space which are closest to a particular point. Even in just the Euclidean metric here, this region here is the Voronoi region associated with that point, because all of the distance to the graph is the minimum distance is to that point. And each element on here has some set of space, some region of space for which it is the closest point. You understand the construction? Yeah? Okay, the very simple RRT heuristic has the property that if you sample randomly, you're going to, on average, the chance of sampling in a region is proportional to the volume of that region. Okay, so you're going to tend to sample in the large regions. The RRT, by the way, does not compute the Voronoi regions. I did that for plotting, but it never does that explicitly. Okay, but with high probability, you're going to pick a large region to begin with. Okay, and then you're going to expand the node that's there. So you're going to tend to make that large region small. So remarkably, without ever computing Voronoi regions, it has this Voronoi bias where it tends to grow out into the large regions, which tend to be in the unexplored space first. But then as the algorithm continues, pause it somewhere here, right? At some point, the bigger regions tend to be the ones on the inside, or they'd just be uniformly across the space. And so it will eventually go in and fill in the details. So it very quickly fills the space, rapidly exploring, okay? But then it'll go through and look at the nooks and crannies as you go to. A really remarkable property that looks like it's coming for free, but I think was a very clever design. Okay, so James was back in the early 2000s was applying it to humanoids. Okay, so how do we solve a planning problem with a humanoid? That's going to be distracting if I leave it up. They're all distracting. Okay, I'll just pause this. All right, humanoid needs to reach under the table. There's two aspects of that problem. One is a very kinematic problem of just finding joint angles that keep the feet flat, okay, and then eventually get down to under the table and are collision free. So the algorithm back in that day was solve a completely kinematic planning problem, but then to make it dynamically feasible, he used the zero moment point, which you all hate, I think, by now, but it's still a good idea. Okay, so he used the zero moment point to filter the trajectories coming out in order to make sure that it was dynamically feasible. As you now know, the zero moment point, so if your velocities are zero, then your center of mass is directly above your center of pressure, your zero moment point, okay? So if you have a trajectory which just respects the fact that the center of mass stays over the feet, then you know that if you run that trajectory arbitrarily slowly, then you'll be safe by the ZMP stability criteria, okay? And then James would speed up the algorithm, speed up the trajectory, okay, so that it was as close as possible to it stayed inside the dynamic criteria of stability. Okay, so as the speed of the execution starts going up, now I've got accelerations of the center of mass. The ZMP will depart from the ground projection of the center of mass and could potentially leave the foot, but I won't speed up till it tips over, okay? And that was a super useful version of the instance of that problem, was just add a little bit of post-processing to include dynamic constraints. Okay, but that's not enough to make it solve like interesting underactuated problems. So let's think about how to do that. If we take this example and we just use it naively, let's say I have some initial state and I only, like a simple modification of the RRT would be to say I'm going to pick a point at random and I'll try to extend towards this point but I'll extend by choosing a U that will move as close as possible to that point over some small amount of time. So instead of just saying I'm allowed to move in a straight line there, if I instead have to find a control action that will, over one step, move me slightly towards the goal, now I can at least expand sort of only feasible trajectories, and I'll start growing things that look more feasible. And that's what I got in the next slide here. Okay, so if I just say the RRT should grow based on closest point, find me an action, now apply that torque for some small amount of time, then it will only expand dynamically feasible things, and it draws these sort of beautiful, it understands the eyeball, right? And will eventually, but a little bit painfully slowly, find a path from the start to the goal. There's a bunch of variants. I didn't tell you all the variants of the RRT. There's too many to even, it's a whole book, and things have progressed a lot since then still. The variant that you're seeing here is you can do a little bit better if you grow a tree both from the start and backwards from the goal. And even in the dynamics setting, I can look at the time reversed system and find a torque that would move me backwards in time in the direction, so you can kind of grow in both directions. And then you have a tree meeting a tree, which is a little bit better than a tree meeting a point. Yeah.
In the example you drew on the board, and I guess this one too, is it Euclidean distance still?
Yes.
So then why doesn't it just end up on the Q axis in the upper right quadrant, like with no velocity? Like, why does it choose to go around?
Yep.
Because that's getting farther away.
Yep. So it's a subtle question, but so let's say I've got some initial part of the tree, and I pick some sample here, and I, sort of mistakenly pick this point. I'm still going to try to pick the closest U that gets me as close as possible. So I'll grow, possibly in the wrong direction, but I'll at least still expand my tree. So the problem that comes up, which you're absolutely right to ask about, is more of a problem of efficiency than about completeness. What you end up doing, for instance, you might expand this node many, many times and put a lot of nodes unnecessarily right on top of each other. And it's sort of, actually, when you watch these things, it's maddening because it just tries to keep expanding the same place and it's not making any progress. But eventually, you'll pick something here and it'll connect up and keep going, right? Yes?
You're still finding the nearest point on the tree by Euclidean distance?
That's right.
Getting it as close as you can.
That's correct. That's under the Euclidean metric. So one of the things we'll be able to do better is to pick a better distance metric. Roughly every step of the algorithm can be imbued with a little bit more dynamics, right? So picking a point at random, we can pick better sampling distributions. Finding the closest point, you can use more dynamics reasoning to find the closest point and have those distance metrics. And then even the operation which chooses the U to extend, we can put more of our dynamic smarts into the notion of an extend. There's basically 3 steps of the algorithm. All of them can be made a little bit better.
Do we still have completeness for any set of dynamics, or is it possible to have cases where you get stuck and the shortest action never takes you towards where you want to go?
It's actually very easy to have probabilistic completeness. It's hard to have efficiency. So I'd be surprised if you lost completeness. You could do things in any of those steps that would lose completeness, but the basic algorithm would be, this one, I think would still be complete, but it would just be very inefficient, right? As long as I have some non-zero probability of taking every action, then I will eventually explore everything. If you get yourself in a situation where where you could actually rule out possible actions, that's where you would potentially lose completeness.
It's complete because you're still sampling your next points at random. You're not trying to go, right? Even if it's not a minimum phase, you're not trying to pull it towards where you want to go. You still sample the space.
This beautiful idea from RRT is to think about picking points at random in the space and using them as a sub-goal. That's really the clever heuristic from RRT, is make random sub-goals and try to grow towards them. So even if you have to go, if you're non-minimum phase, you have to go that way before you go this way, you'll eventually sample this way, go there, and then go that way. So it can solve non-minimum phase problems. Okay, so I think you guys basically forecasted the recipe. Let's think about the 3 basic steps of the algorithm. We're going to choose Q at random, right? And here we're going to try to improve the sampling distributions. We're going to find the nearest neighbor, find the closest point on the tree. Here we want to have better distance metrics. And then we need to extend the tree from Q near towards Q random. We can do better extend operations. Okay. I think it's actually, since you guys were asking a lot about the distance metrics, I'll do the distance metric first. I think that's a good one to start with. So given this sort of problem, what's sort of the right distance metric to talk about how close some point is to some other point? Knowing everything we've talked about in the class so far, what do you think would be kind of a better, I mean, the Euclidean distance, we just saw its deficiencies, we understand that, but what would be a good distance metric? Yeah. Like a cost to go, right? So we have all the tools from dynamic programming. Were you going to say the same? Yeah. For what cost function? We still have to pick a cost function.
Min time.
Minimum time seems like a perfectly reasonable, right? I don't know that there's a right answer for that question, but I think if you don't know anything better, minimum time seems less biased than, I don't know, than some arbitrary cost function. Yeah.
If you're going to end up controlling it with LQR, you're going to try to use the same weightings as.
Okay, good. So he asks if you're going to eventually control it with LQR, then what maybe that should come into your distance metric early on, right? Right. So that gets a little bit towards the story here, which is that if we could solve the cost to go for the minimum time problem from every point to every point, then we probably didn't need to use the RRT in the first place. Okay. So there's a tension here of trying to use the dynamics knowledge to solve the problem, but also not having to solve the entire long-term planning problem in order to give ourselves a distance metric. Okay, so we're going to be in the game of using approximate distance metrics, right? Maybe locally good distance metrics. We'll come back to LQR as a possible way to do that. For instance, you could try to compute LQR solutions locally to define some local notion of distance, which would be like the cost to go of the LQR. Right, that's a reasonable thing. It's not great for minimum time, but we can ask about that. Okay, so but there's other versions of this too. My favorite one of all time was actually Emilio Frazzoli used to be a faculty here. He moved to ETH Zurich. I guess it's a nice place to live. And his thesis actually, I think, captured so well a very beautiful idea of how to combine sort of the sample-based motion planning, distance metrics, and the like with dynamics. And it was very simple. Let me see if I can tell it in pictures first before we do it. He talked about real-time motion planning for agile autonomous vehicles. And actually, the algorithm sort of captures it. So pick a configuration at random, try to expand all the nodes in the tree in order of increasing cost, J star. Okay, that's roughly what we just said would be a good idea. And then apply the optimal control policy. Okay, but the clever thing is he was thinking about helicopters flying around obstacles back at the time. And the beautiful idea he had is that maybe I can offline use value iteration. We used the same value iteration algorithm we've talked about to compute the cost to go for the it's a helicopter back in the day. Quadrotors weren't a thing yet. Okay, when there's no constraints, there's no trees, and then use that as a heuristic to introduce paths around the trees. Is that sort of clear? You can't afford to solve every real-time motion planning problem with every tree, but maybe in cases where it's like 6 dimensions or less, you can solve the brute force case once and then use the unconstrained thing as a distance metric for the constrained one. Okay, and I just think that's such a beautiful version of the problem. So he had now beautiful trajectories of the helicopter that you'd sample at random. You would look at it's a little bit expensive, right? So you take the goal state here. You have to use some observations that you can translate and rotate the cost to go function based on some of the invariance of the helicopter. You need for any state to be the goal, you need your pre-computed cost to go function to be pointing to that state. Luckily, like helicopters, if you rotate them, the dynamics are the same. So if you have a cost to go function that's in some coordinate and you want to rotate the goal, you can just rotate the cost to go function. Similarly in translation, right? Those don't affect the dynamics, so you can just there's some trivial invariance in the problem that allows him to move the cost to go function around. Okay, so if I have the goal here, then you compute the cost to go from all the other samples in the tree, then it'll figure out that this was the closest state and grow from there. That was maybe a bad example because there's only one choice, but farther along the tree, it's still doing the same thing. The other observation that he made, which is buried in the slightly heavy text there, is that if you have the optimal policy associated with the original quadrotor, then you can also use that to make a better extend operation. So if I pick this, I say this is my closest point, I can just run the optimal policy to get me there. Okay? And then when I'm going here, I might pick a sample that was unaware of the tree. It says this, but I will exclude that because the path would have been collision-free. And eventually, with high enough probability, I would have sampled some points over here and grown the tree over here and gotten one that was closer. Okay? Any questions about that? Yeah?
Can you explain heuristic versus metric? We were talking about like distance metrics over here and then
He uses the word heuristic in here?
yeah, on 2, sort of the node metric or the desired heuristics.
Aha. Random versus exploration versus... There's a number of ways that people use the word heuristic in search. That's actually doesn't look like the one I expected when I turned my head. Yeah, so in the variance of RRTs and things like this, there are, I think, a number of heuristics, I guess, for instance, if you know you want to get to a particular goal, then you might pick a point at random with high probability, but with some small probability, pick the goal so that you have a goal-directed, you have a bias towards not just exploring all of the space, but sort of directing yourself towards the goal. Similarly, you can put in different, so that might be random versus, exploration versus random or optimization, I guess it might be that. I'd have to actually look back at the paper to know exactly what he did there. There are other ways too where you can inject a cost function in the way that you grow your samples. I think he means that. Yeah. I'm sorry, I didn't remember the exact words, yeah.
So for example, from point 2 and then extending towards the random point, but you hit the obstacle. So in this case, do you just like throw away, like you don't do that step? Whereas in the pendulum example you showed us earlier, you would still extend, just like not really that way. Is that right? That's the difference.
Exactly right. So one of the heavy ideas that people use in sampling-based motion planning is that if there can be a very hard to sample from distribution, but if you do rejection sampling, then it's actually a very clever, slightly inefficient, but clever way to sample from a difficult distribution, right? So you want to sample from the points that are actually reachable. So the way to do it is ignore the collisions, sample and then just remove the ones that were there, and and the effect is that you get a sampling distribution that looks like the reachable regions. Yeah. It's a very heavily used idea throughout this literature. Yeah.
I guess like as this algorithm is getting more complicated, could you go over again why trajectory optimization would be suitable for this?
Okay. So you could definitely, if I pick a point at random and I'm able to pick an initial state, you could imagine doing trajectory optimization for the extend operation. That's one good way, reasonably good way, but expensive way potentially to do this third operation. I'll talk about a slightly nuanced version of that if we have time. The trajectory optimization would be very expensive if you wanted to use that for the distance metric, because you might have to solve the trajectory optimization from every other point. That's probably more than you'd want to do. Okay. In general, these trees tend to grow, tens of thousands of nodes. So the people who have put trajectory optimization in there work really hard to try to make the simplest, the fastest possible trajectory optimization. And even still, they're slow compared to the non-trajectory optimization versions. But in terms of like being efficient, I think there's no conceptual problem. It's just an amount of, it's a numerical efficiency question.
If our system doesn't have the sorts of invariances that like a helicopter or quad rotor has, are we just out of luck?
I think the idea holds. Maybe we can use different approximate cost to goes, right? I think the trivial invariances made it so that the brute force one-time cost to go could work in many situations, right? I think if you were to not have those invariances, you might have to solve a small approximate dynamic programming problem in order to get something similar, right? Since you guys seem to like that one, let me just say how you could do that. If you did want to solve, people have done that, for instance. We did a version of it. It's actually kind of funny because we tried to do it right. We tried to solve the minimum time LQR problem, which is slightly expensive, but it's sort of correct because you can't write LQR as a time invariant LQR at a non-fixed point. You guys know that. You can write finite time LQR, and you can define minimum time cost to go for a non-zero fixed point. Okay, so there was a early paper that we wrote about doing minimum time LQR for approximate distance metrics. Okay, I think that is a sound and good thing to do. It's a sort of less than trajectory optimization because you can have a cost to go for the entire space, okay, but still slightly expensive. And then you could there's something called the LQR RRT, and there's actually an RRT star version of that too, which is quite popular, which it kind of drives me nuts, but it just kind of says, pick the point, pretend it's a fixed point, solve the time invariant thing, and use the cost to go from that, which is an easier computation. It's wrong when you have large velocity, but it's maybe a good enough heuristic that it helps power some things through. Okay, so the picture there then would be that you would have, like imagine I sampled something that was a fixed point, right? So I have my cost to go function like this, and that would properly then try to grow. It would say that the nearest points are something like this, right? But more generally, you can solve the minimum time LQR problem. We have various versions of it. In the LQR chapter, I don't know if you noticed, but I have like at the bottom all kinds of variants of LQR, and there's many, and there's even more that every time I stumble upon a new one, I'm like, oh, I should add that for completeness or whatever. I just the other day saw the binary control input LQR has a nice solution. Okay, but there's a version of that is the minimum time LQR, where you have the cost function is 1 plus, the cost function for this is 1 plus okay, and if you're stabilizing a non-stable point, then you want to have the time varying linearization. So that has this a nice solution where you can actually grow backwards in time. What's the right cost to go function for all of the states? And you'd expect it to be accurate in the vicinity where your linearization is good. And that actually is a pretty good way to do an approximate heuristic that doesn't require invariance in the fixed points. Emilio also made a few other really, I think, important points in that work. So first of all, I think, so he did only grow in positions and, and move from position to position because that's what his cost to go worked for. But maybe there's some sense in which that's the right thing to do. He talked about these segments being trims and maneuvers that were connecting, relatively otherwise good points. And he also, I think if he saw me talking about this, would say, writing this, trying to grow an RRT for this potentially uncontrolled system might lead to sort of wild expansion, and that's not actually what you'd like to do. If you do have a controller, even a simple controller, a PD controller or something like this that can help regulate the system, that it might actually make sense to try to do randomized planning through the system that is the combination of your unstable system with your stabilizing system, right? So if you have the option of thinking about the quadrotor dynamics, think about this as, x of t, and this is my dynamics going through here. It can often be better to write a very simple sort of stabilizing controller which maybe has some inputs to the, let's say x desired of t coming into the controller, and you might be better off doing randomized motion planning and using all of our control ideas and heuristics on this system rather than the original system. Unstable systems have the way of squirreling off into lots of different directions, but a controlled system can be numerically better behaved. Cool, so you guys mostly predicted that one, but that's a pretty good one. Any ideas for how to pick a better sampling distribution? We've got lots of tools from the class. How would you pick a better sampling distribution? Think about the Lyapunov days. Maybe that'll push you in a direction. I think there's many ways you could make a better sampling distribution, but one I particularly like that I'll tell you about has some connections to Lyapunov.
Sums of squares.
Sums of squares. No, I mean, that's not just sums of squares, but I thank you for feeding that for me. You could, so okay, that's a good question. So how could I use a sums of squares sort of recipe to somehow put a distribution? There actually are deep connections between sums of squares and density functions and distributions. That's probably a really good answer, actually, in some cases, but not in the sums of squares problems we've written so far. That's not immediately what I'm thinking. Well, they're connected. They're connected. All right, let me tell you one idea. It's not the only one, but I think a nice connection to what we've seen before. That's the connection to Lyapunov. Okay. Sam actually sort of said it when he asked about this example here. So the frustrating thing about watching this grow is that if I pick samples that are where the distance metric is bad, then it will continually try to grow into in a direction where you can't get to the sample. I think what you'd really like would be to somehow have a sense for where the tree could grow. What are the frontiers that are dynamically feasible? And try to sample from that distribution. Okay, so here's the basic RRT. Here's a reachability guided RRT. I think I have an image here that sort of tells that story. There's very approximate ways to do it. I'll tell you about that one in a second. That's not the picture I wanted. I think I forgot to include the slide of what if we could somehow take our initial tree I've got some initially grown tree, and if I could, for every point on the tree, have some sort of sense of that, we know that for different U's, this would be like U. These are the different possible U's, right? There's some set of states that are reachable in one step from this node. And there's a bunch of sets that are reachable from this node. And what we should sort of have is everywhere a sense of the reachable space. And what we'd like to do is, if I have samples that are outside the reachable set, I either reject them or somehow project them back into the local reachable thing. So if I could perfectly compute reachable sets for every point on the tree, then I think rejection sampling would be a beautiful way to shape the distribution. I could just say, if I'm inside somebody's reachable set, then not only, then I'll keep it. If I'm outside, I'll reject it. And when I've found the reachable set, then I know I can grow, and I have even the algorithm for growing the tree perfectly towards that. Computing the exact reachability, we could use sums of squares for every sample from every point. That might be expensive. So again, we end up playing games of trying to do approximate reachability, right? And then hoping that the power of the sampling will eventually overcome the shortcomings of our reachability analysis. Yeah?
So you wouldn't have to check for collisions with this then, right? 'Cause already within reachability.
That's a great question. So would I have to check for collisions? So if my reachability computation included the collisions, then I wouldn't. But if it's an approximate thing, then maybe I still did do some checks. So if I did reachability computation, kind of like Amelia, but without ignoring the collisions, maybe that's a simpler problem to solve, but then I still do the collision checks. Right, so the game becomes using your full dynamics knowledge, which in the brute force would be solving the entire search problem, versus local approximations. So people have done things like local linear approximations of the reachable set. That's a fairly easy computation. And for linear dynamical systems, if you have boxes of possible U's, if U is just saturated, then there's actually, we know how to write those sets exactly. We have a polytopic sets that are the reachable sets. Sorry, you have first, yeah?
Yes, so does that mean instead of now having all the samples is distributed over the space, now that you would move from one location, and then every time you make a distribution based on that location? You go from there.
So here's a straw man proposal, which would be that every time I add a node to the tree, I'll do a little work to compute this region, right? And then every time I sample, I will check if I'm in the region for all of the nodes. That might be expensive, but that's kind of what I'm working on. That's the basic algorithm I'm proposing here. Did you have that's the same question, yeah? Yes?
Beforehand, you were taking points that were outside of one step, and you were growing it one step worth towards that point. Now, if you're picking it within one step, are you going to end up short, or are you going to go one step in whatever direction it ends up?
Okay, so this is great. So I think what you're asking is the subtleties of time, maybe, in this, right? So actually, I drew it like this cone that goes out from here. If I'm allowed to extend for any duration between 0 and delta t, let's say, then it really would look like a cone. If I'm saying exactly delta t, then it would actually look more like a shadow over here, and you wouldn't be able to visit those nodes. So we try to do, even though the easier reachability computation would be to where could I be at exactly, let's say 0.1 seconds from now, we want to probably solve the, for any 0 to capital, or to 0.1 seconds, what is the reachable set? And then index into time that way. Unless your system is constrained that it can't take smaller steps. Is that what you were asking?
Kind of. In the previous one, you took a point outside of that region in one step, right? And then you went, or just put it forward.
Oh, okay, yep.
Yeah. And now you went forward to the end of the cone towards it.
I see, okay, right. So, good. You could try to do that. I don't know how to do that as well. I mean, you could think about trying to write a projection of this that would allow you to do that and try to, even if a point was here, it would know to grow here. The very approximate algorithm that was appearing on the next slide does have that property. I don't know if it's how to do that in general necessarily. Okay, so this general class of algorithms is called reachability guided RRT. If it's added to the RRT, one of the first versions of that used a very clever, very coarse approximation of what this would, of how to compute these reachable sets. It didn't use sums of squares. It didn't even use linear dynamical systems. It just used a very clever heuristic, which said every time that I grow a node, add a node to the tree, what I'll do is I'll immediately fire off samples at all of the maximum, at all the corners of my allowable U, okay? So he grows 2 trees, okay? The nominal tree, which is our nominal plan, and a tree representing the potentially reachable states, okay? And then when you sample a new point, you ask, you check both trees. If the point that you're closest to is one of the green, the reachable tree, then you look at its parent and you expand from here, which has this, it does actually accomplish this projection that you wanted to, okay? The sampling in all the corners is not a great way to compute the reachable set, but it's a very fast, easy approximation, okay? And then if you were to find that this node was the closest, that you basically already, your yellow tree is as close to this point as any of the reachable things, then you don't bother to expand and you just call that a rejection sample. If you look at the Voronoi regions then of growth for that sort of for that very simple algorithm, you get this thing that I started to show, okay? So when it starts, it has, the Voronoi regions are sort of almost everywhere, so it encourages growth. But as it proceeds, it tends to only draw samples that will cause the tree to expand, using a very simple heuristic for the approximate reachability. Right? The higher dimensional your system, the more nonlinear it is, the less appealing that is as a heuristic, but it's surprisingly good. To the point where that was how, back in the day, we used RRTs to find bounding gaits for little dog bouncing over rough terrain, okay? So in this case, the system, it was a bit like this picture here. We actually had a very simple controller that would run for a small amount of seconds, not like 0.1 seconds, but for some duration that would kind of rock the quadruped back or forth. And we would sample in this the reachable set and potentially grow the tree. One of the nice things about that simple algorithm is that it even worked on the hybrid system, okay? So if you look at the picture that we've talked about for hybrid systems, right, one of the classical problems with the hybrid system picture is that this, we don't normally know how to write a distance metric that goes across this sort of wormhole, right? Which the coordinates could be different, all of these things could be very different. So we don't have general algorithms for writing, you know, for saying, if I sampled here, I should grow from here. Okay, but if you do this sort of very simple reachable set computation, then this node here might expand into reachable regions over here, and that actually does give you information. If you sampled here, it'll tell you that I should actually grow here and grow through contact. Okay, so that was a pretty effective version of the algorithm. Yeah.
Do you never sample? So the case where you sample a point, the nearest point is yellow, but this yellow point was already expanded at some point, so we have the two. Wouldn't that, suppose that I really need to go through that yellow point to my target,
Yep.
except I want to oversample it again. It seems undesirable.
The only thing, so what happens is if I were to sample this and then try to grow exactly there, if I have points, we give precedence to the yellow over the green. So if that is the closest point, then it won't grow that again. But when I added this node, I also added these. So you can still grow from that yellow, you just won't grow from the points that are closer to that yellow than to these green. I think that's exactly the intention. Is there a trap that you're worried about that doesn't?
I'll draw it up.
Okay. Yeah. Okay, I won't have time to say it in detail, but you absolutely can do the better extend operation using trajectory optimization. That is a place where I think trajectory optimization snaps right in. Maybe I'll just give you the one high-level picture of it that I think is useful. Okay, so imagine I've got a, I like to think of it going backwards from the goal. Maybe I have long, beautiful branches of my tree because I've been using trajectory optimization to do all my connection steps. Okay, and now I sample a new point, and I use one of my favorite distance metrics, but I want to grow to the tree. Trajectory optimization can be used to go from you know, if I say this is the closest point on the tree, or maybe this one is the closest point on the tree even, right? I could write a trajectory optimization that just says, find me a trajectory that goes from the start to the goal, but I will often find myself infeasible because my distance metric is bad and all these other things. Slightly more interesting is to say, find me a path from the start to the tree. You can write a constraint saying the final state must be anywhere on the tree. If these are described by piecewise polynomial trajectories, you can actually write that constraint nicely. It'll have a logical condition about which segment you're closest to on the tree, but you could write that. And you can seed it with an initial guess that is trying to go there, but the solver might be strong enough to actually, if you seed it with that, to actually realize it could connect somewhere halfway along this branch of the tree and connect up nicely and follow that on the way in. Using trajectory optimization with that richer final constraint makes a huge difference in the power of a trajectory optimization for growing out and overcoming initially bad distance metrics and sampling distributions. Okay? So that's maybe my favorite way to use the trajectory optimization to do better things. Okay, that's a whirlwind of sampling-based motion planning. Let me just say that there are there's powerful libraries of sampling-based motion planning that you might find useful. OMPL is it's getting a little bit old now, but I think there's the authors are thinking about having an OMPL2 maybe coming out soon. Okay, but a lot of people lean on the open motion planning library. It's got, and I'd say a lot of papers now, it's got enough of the algorithms implemented in it that it serves as benchmarks, and then new papers getting reviewed. It's like, did you compare it against OMPL? Yes or no, right? And if you look at the list of available planners in OMPL, you'll see there's a lot of geometric-only planners, like the PRM, okay? There's the RRT, And then they specifically call out, if you scroll down, planners that can take an objective versus ones that don't. And control-based planners, which is what they're calling ones that have subject to dynamic constraints. Okay, and so there's a handful of these that are capable of taking some amount of dynamic constraints, RRT being the first, right? But there's a library of these things, and there's many, many variants that have come out in the literature. Good. We'll dig a little deeper into the optimization version of the planning around obstacles on Tuesday.